again, one of those two.
Thank you.
Okay, on the previous assignment, I graded a couple of them, and on the couple I graded, I did put a comment about work on some of them, and you may be wondering, well, what kind of work could we do? So, say example 23, sketch a graph for the rate. And we could, especially if it was in front of us, draw in some little tangent lines and estimate what the slope is. So we can definitely kind of tell where the slope is 0 to identify where the slope is negative. So it's kind of hard to tell exactly what work could be done, but there is some work that could be done to kind of indicate what you were thinking as you did that. And on an exam, if I see the work and your answer doesn't look close to what I was expecting, I can look at the work to figure out what were you thinking. If it's close to what I was expecting, you wouldn't have to have the work on something like this, but definitely having the work is to your benefit to indicate you do understand what's going on. So, 2.3 then we looked at some rules for finding the derivative. So that was so questions from the problems here. 6. So 6, we've got the function f of x is x cubed plus 9x squared minus 6, or plus 6. And we want to calculate f prime and determine when f prime is 0. So f prime of 1, and figure out where f prime of x equals 0. They say determine, I would more aptly call that solve. So just like with other functions, we're evaluating and we're solving. What's a little different here is we have to do a little bit more work before we evaluate or solve. We're either evaluating at 1 or solving where it's 0, but first we've got to figure out, well, what is that function? Because we're doing this for the derivative, not the original function. So for the derivative, we take the derivative term by term by term. So the derivative here, 3x squared plus 9 times 2x. In each case, using the power rule, x to a power, the derivative is the power times x to the power minus 1. And then the derivative of the constant is 0. So our derivative here is 3x squared plus 18x. That's what the derivative is in general. Evaluating it then at 1, when we plug 1 into this function, we get 21. Solve, we've got to figure out, okay, where is this function equal to 0? Didn't get to an example like that, but we've done other examples where we've been trying to solve functions. So it's the same idea here, and the fact we're looking to solve where it's equal to 0 is not coincidental. That's the case we are, in fact, going to be the most interested in, where the derivative is 0. So I can factor out, let's see, a 3x. And so either one factor is 0 or the other factor is 0. So x is either 0 or negative 6. That would give us where the derivative is 0. And today we're going to pursue this idea a little bit more, because in 2.2 we were going from the function to information about the derivative. Where the derivative was positive, where it was negative, and where it was 0. And so we could go from the graph of a function and determine where the derivative is positive, where the derivative was 0, where the derivative was negative, and where the derivative was 0 again. Turns out we can go the other way as well. If we can figure out where the derivative is 0, and in some cases we can. We just did that here. Then we know where the function is leveled off. And that would help us graph the function. So in fact, if we even kind of start thinking about that right now, what we've discovered for this particular function, the function levels off at x equals 0 and x equals -6. At x equals 0, the function 0 plus 0 plus 6, the function goes through 6. So we know the function goes through that point, and in fact we also know what direction it's headed. The slope of the tangent line is 0 right there. What about at -6? F of -6, -6 cubed, plus 9 times -6 squared, plus 6. I think 9 times 6 squared is 324. We can pull out our calculator to make sure we've got the computations correct, but I think we're going through 114. So over here at -6, we're way up here at 114. The important thing, we could do that, but the slope of the tangent line is 0 there. From those bits of information, at what values of x is the derivative 0? What is the value for y where that derivative is 0? That gives us 2 points, and from those two, we can do a fairly reasonable job of sketching this. Certainly, from here to here, about the only possibility is that the graph's going to have to look something like that. If we assume, and we will analyze the derivative further in a couple days, that it kind of changes direction wherever it levels off, we then have some idea of what the graph looks like. We found that the 2 key points, the 2 most interesting points on this function happens to be where the function levels off. And so if we don't trust our graph, and we pull out a graphing utility, so we come here and pull out a graphing utility and graph this function. So this function was x cubed plus 9x squared plus 6. We'd identified 2 key points, 0, 6. And notice 0, 6 is where it levels off, and -614. Which notice happens to be the other place this graph levels off. And we knew that before we asked the graphing utility to do it. So information about the derivative, which we can find, where it's 0, is going to help us actually come up with the graph. So we're very much moving toward reversing what we did in 2.2 of the graph of the function telling us stuff about the derivative. We're headed toward the derivative is going to tell us stuff about the graph of the function. So we can actually graph the function. Or figure out the peaks and valleys without even graphing the function. Just because of analyzing the derivative, we can figure out the peaks and valleys. So it's a couple more days before we officially get to that, but part of our challenge as we work with the derivative is to kind of keep straight how are we doing it and what are we really going to do with it. So one of our interpretations definitely is the slope of the tangent line. And for where we're headed long term, knowing where that slope is 0 is extremely important for us. Okay, other questions? And I went far beyond what those questions originally asked for. This is all it asked for originally. 7? So 7, we get another one. Where we're looking to evaluate the function and to solve. It's a different function. So in 7, our function is x cubed plus 3x squared plus 3x minus 1. So the derivative, 3x squared, 3 times 2x, and then the linear is just the slope of the linear. So we can do it piece by piece by piece. As long as we're adding the pieces or subtracting the pieces, we can do piece by piece by piece. Constant multiples, it's still the constant multiple times the derivative of the piece. And so we get here 3x squared plus 6x plus 3. And so at 1, this is 3 times 1 squared plus 6 times 1 plus 3, I think equals 12. Solving where the derivative is 0. We set our function equal to 0, and we try to solve it. It's a quadratic. We could go to the quadratic formula. We could attempt to factor it. Anybody see anything that does factor with this? We can pull out a 3, I think, can't we? 3 times x squared plus 2x plus 1. The 3 is not going to give us the 0, but this now at least looks a little bit more typical of things we factor. We're much better at factoring when it's an x squared, not so much when it's a 3x squared. That actually factors into x plus 1 times x plus 1. And so here only at x equals -1 is where we expect the slope of the tangent line to be 0. And so again, we know a little bit about this curve. Here we actually know less than we did the previous one, because we only know right at x equals -1. So if we started thinking about this curve at x equals -1, the function f of -1, -1 cubed, plus 3 times -1 squared, plus 3 times -1 minus 1, I think is -2. At this point, that's about all we know. The curve goes through that point, and when it goes through that point, the tangent line is horizontal. And since we've only got the 1, we really don't have any other points to connect to even get a sense of what the graph might look like. So here is definitely a case. If there are other things the derivative can tell us, it would be nice to know that, so we can use the derivative to give us other bits of information. I think Thursday, when we get back after spring break, we'll incorporate that information. But certainly we know just a little bit about the graph. And if we pull out our graphing utility and look at it, let me turn these all off. We've decided something interesting is happening at the point -1, -2. Go back to a slightly more typical viewing window, and our function here is x cubed plus 3x squared plus 3x minus 1. And notice, the function does go through that point, and the tangent line is horizontal at that point. Now, it definitely looks different than the previous one, because actually there is something different going on here, and in a couple days when we look closer at other parts of the derivative, we can figure out that the graph's going to look like that. But at this point, the reason we're interested in where the tangent line is horizontal, or where the slope is 0, is that does give us some vital information about the graph, which will help us graph it, will help us find the peaks and valleys, because that's the question we're very interested in. When we got the graph, we can see the peaks and valleys. The problem is, if we're starting with the rule, unless we graph really precisely, we don't know where the peaks and valleys are. The derivative is going to help us figure out where those peaks and valleys are. Okay. Other questions? Two? Any particular part of 2?
All of them.
Okay. I mean, in all of them, we're looking to find the derivative. There are some different notations, and the reason there are multiple notations, historically different people developed calculus, and each had their own notation, and so there are times we just see different notations. So we've got in A, the derivative of x to the 12th. Well, that's a straight power rule. Derivative of x to a power, the derivative is the power times x to the power minus 1. So it's 12 times x to the 11th. B, the derivative with respect to x of the 7th root of x, at first glance doesn't look like a power until we remember, wait a minute, the radical could be written in terms of a fractional exponent. So no derivative yet, we're just rewriting this, the 7th root of x, that is x to the 1/7 power. And now the power rule applies. Derivative of x to a power, we can bring the power down and subtract 1 from the power. Now, with the fraction, subtracting 1 from the power is a bit more complicated as well. One is 7/7, and so 1/7 minus 7/7, we get here negative 6/7. And here's a case we would go ahead and leave the negative power in there. I don't think we could convert back to a radical. Since we converted to fractional exponents, I would just leave it as fractional exponents. The third one, the derivative of 1 over x cubed. This one also, as written, doesn't really look like x to a power. I mean, e to the x, x to a power, log of x, those are the functions we know how to do right now. Most of the time in algebra, we want to write expressions like this, but there is another form we could write this expression. We could use a negative power. 1 over x cubed is x to the negative 3rd. And so again, we've not done the derivative yet, we've just changed the form of our function, so now it's a form that we can actually use the power rule on. Derivative of x to a power, we bring the power down, we decrease the power by 1. So we get here negative 3 x to the negative 4th. This one actually, that form would be fine, or we could go back to the form where we don't have the negative power in there. Put it back in terms of a division. And then D, we've got the derivative of x to the e power with respect to x, just another notation for taking the derivative of x to the e. Well, e is some number. We're not really all that comfortable with what number it is, but it is a fixed number, 2.718 something. So it also fits the power rule. Derivative of x to a power is the power times x to the power minus 1. And we would just leave it that way. So the power doesn't have to be an integer. It can be a fraction. It doesn't have to be positive. It can be negative. It doesn't even have to be an integer or a fraction. It could be some strange number. As long as it's x to a power, the derivative of x to a power is always the power times x to the power minus 1. And that's true for any power except the 0th power. I mean, x to the 0th power is 1. We have another rule for the derivative of a constant. We don't apply the power rule, although I guess even if we think the power rule, x to the 0, we get 0. Doesn't really matter what the rest is. The derivative is 0. So in terms of the derivative, even for constants, we can think of it as x to a power and use the power rule. Okay. I want to move on and try to get 2-3 finished and also 2-4. 2-4 gets a couple more rules. 2-3 we're going to revisit what exactly is the derivative telling us, or what are some of the things the derivative could be telling us. So if you've got your homework and you're ready to turn that in now, that's fine, or you can bring it by later. So we now have an easier way to find the derivative. At least if it's a fairly simple function, we've got an easier way to find the derivative. Power, if it's just x to a power, we've got the power rule. If we're adding or subtracting expressions like that, e to the x, we've got the derivative for. Log, we've got the derivative for. So we're going to return to think about, okay, what again is the derivative telling us? Well, the book gives actually quite a few different interpretations of the derivative. Different ways we might use the derivative. We'll cover quite a few of these, and I think we'll have time to cover most of them, and then hopefully get to 2-4, where we get a couple more complicated rules on how we find the derivative. Because the function could be more complicated than just adding up some pieces. So, our first interpretation, it's the slope of the tangent line. So if we had a curve, y equals 2e to the x plus x, and we're at x equals 0, we should be able to figure out the slope of the tangent line by taking the derivative. So for this particular function, what is the derivative? So we've got a sum, we take the derivative piece by piece. So this would actually be 2 times the derivative of e to the x plus the derivative of x. Derivative of a linear is just the slope. Derivative of e to the x is actually just e to the x. So our derivative here is 2 times e to the x plus 1, which was c. So we take the derivative of each piece. At x equals 0, the function itself, we plug 0 in. Oh. At 0, for the derivative, we plug 0 into the derivative. Y prime equals 2 times e to the 0 plus 1. Anything to the 0th power is 1. So 2 times 1 plus 1 is 3. So that tells us the slope of the tangent line is 3. The point on the curve. At x equals 0, the point on the curve, y is 2 times e to the 0 plus 0. The point on the curve is 2. So what we know at this point about this curve, we go through the point 0, 2, and we know we're going through with a slope of about 3. Well, a slope of 3, not about 3. We figured that out exactly. Well, if we know the slope, and in this case what we happen to know is the y-intercept, we actually know the equation of the tangent line. What's the equation of the tangent line going to be? And in fact, at this point, we don't have to know it's the tangent line, the equation of any line. If we're told the slope and a point it goes through, we should be able to figure out the equation of that line. So we have a slope, we have a point we go through. In fact, it happens to be the y-intercept we're going through in this case. We should be able to come up with the equation. And it is y equals the slope times x plus the y-intercept. So in this case, it is y equals 3x plus 2. In general, y equals mx plus b. We have our slope. We have our y-intercept because we were doing this at x equals 0. So we know the equation of this line. So again, let's go and let's graph a few things. So we've got the point 0, 2. That should be a point on the curve. We've decided the equation of the tangent line is y equals 3x plus 2. So nearby 0, 2, the curve should look like that line. Well, let's see if it does. Let's ask this to graph y equals 2 e to the x plus x. And notice the graph does go through 0, 2, and it really is going through in this direction. And as long as we don't move very far, an approximation along the tangent line is a pretty good approximation for the curve itself. And we can do an approximation along the tangent line. It's just a simple evaluation. This is a much less simple evaluation. So if we want to know, say, what happens when we get over to a half. Yes, I can pull out my calculator and figure out what happens at a half. I don't have to on the tangent line. The tangent line y equals 3x plus 2. When x is a half, I don't need my calculator for that computation. I might still like it, but I don't have to have it. We're at 3.5. That's the point on the tangent line. And notice that point is still pretty close to the actual point on the curve. But I can figure out the point on the tangent line much easier than I can figure out the actual point on the curve. And so one of our uses of the tangent line is going to be to help us approximate this function. As long as we don't go very far, working with the tangent line is a whole lot easier than working with the function. In fact, that's the whole idea behind the marginal cost. Let's change the input by 1. If we move along the tangent line, if I change the input by 1 here, the output changes by the slope. In this case, we've discovered that's 3. So we go up from 0, 2 to 1, 5. 1, 5 would be another point on the tangent line. Now in this case, it's not all that close necessarily to the point on the curve. But it's a whole lot easier to make that computation than it is to actually ask the calculator, what is the value exactly? And so we just kind of make the assumption, yes, we know the curve is going at a different rate, but right at 0, we know the rate of change. And if we assume that's the rate of change that continues, change of input in 1, the output changes by 3, that's a reasonable approximation for what happens in that next step. And that's the idea of the marginal cost. What would it cost to produce the next one? In this case, $3. This is not a really good function to illustrate for costs, because normally, if you're talking costs, you would expect the cost to kind of level out. You know, as you start producing more, it costs less to produce the next one. The exponential is actually the exact opposite. The more you produce, the more it costs to produce the next one, because it grows faster and faster and faster. Now, another interpretation that we've talked a little bit about, besides the slope of the tangent line, is the instantaneous velocity. If our graph is height over time, the slope of the tangent line is the instantaneous velocity. How much does the height change over time? Well, now that we've got a way to compute this derivative more readily, the derivative is the velocity. Knowing the velocity is going to tell us some things. So we've got this function, h of x, negative 16 x squared plus 128x. And in fact, they kind of give us a graph. It doesn't have it doesn't have any axis markings in terms of how high we go and how long we're in the air. In fact, that's some of the questions we're going to be asked as we work through this problem. But when we think velocity, the velocity is the derivative of the position. That's another interpretation of our derivative. If we're talking position or height, the velocity is found by taking the derivative. So, actually we're going to look at number 13, which is the same type thing, it just changes our function. So we're actually going to look at 13. You get to do number 12 in your homework. So negative 2.65 x squared plus 128x. And they want us to do these parts A through E. And it says here problem 40, and it's really that problem. There was an error in the book because they were rearranging where problems were. So the first thing we've got to do is we've got this height function, we've got to figure out the velocity. What is going to tell us the velocity? Is it the first derivative, the second derivative, the function itself, or do we just not have a way to tell the velocity? Well, most of you caught what I said. In fact, I have written here, the velocity is the first derivative. The function itself is what we have graphed. The second derivative actually is important in some case, and I think we'll talk about that in a little bit, but we actually can tell. If we're given the position at any time, we can figure out the velocity, and that's another interpretation of the derivative. It's the velocity. So for this particular function, what is our velocity going to be? What is that derivative going to be? We've got our function. What's the derivative going to be? We take the derivative term by term. So we got negative 2.65, derivative of x squared is 2x to the first power, and the derivative of 128 times x is just 128. And so double this, we do get negative 5.3x plus 128, which was d here. So we can compute the velocity. Might also add at this point, if you're wondering, well, where did they come up with this function in the first place? In calculus 1, we would look at where we come up with that. In business calculus, we're just going to accept the function they've given us. This is what's describing the height, and we're going to try to analyze it. And we start our analysis by figuring out the velocity. And once we know the velocity in general, we can figure out what is the velocity at 0, what's the velocity at 1, what's the velocity at 2, how fast are we moving at each of those times. The next question then is, well, when does this stop? Because the velocity, we are going up for a while, we're going to stop. And so, as we look for where it stops, what are we trying to figure out about the velocity? Are we trying to figure out where it's positive, where it's 0, or where it's negative? Well, when it stops, the velocity is 0. If the velocity is still positive, we're still moving up. Once the velocity is negative, we're moving down. We are looking for that instant when it stops, when the velocity is 0. Similarly, if we went out and watched at the stop sign here, we'd be looking to see exactly when people stop, and probably discovering that most do not stop. They slow down quite a bit, they see nobody's coming, and then they keep going. We call that, what, a rolling stop? That's the way a lot of us take our stop signs, is sort of a rolling stop. We don't just stop, make sure that we're not moving at all, and then go again. But in this case, when it is heading up, at some point it will stop, and then it will start coming back down. So, we need to figure out where the velocity is 0. So we need to find where the velocity equals 0, and so we need to solve where is this function equal to 0. Not the height function, but the velocity function. And that's another thing we're going to kind of have to keep straight as we work through these problems, because we're going to go back and forth between the function and the velocity. Sometimes we're interested in the height, other times we're interested in the velocity. Height, velocity, and times at which that's happening. So here we're interested in the velocity. Where is the velocity? 0. So we set our velocity function equal to 0. Can we solve that? Takes a little bit of work, but we can subtract 128 from both sides. We can divide both sides by the negative 5.3. And I think when we do that, we come up with x is 24.15 seconds. So we've got this graph. We now know where the velocity is 0, or in terms of the graph, where the tangent line is horizontal. The velocity and the slope of the tangent line are the same. In here, we're really thinking velocity, but when we look at the graph, it's still the slope of the tangent line. So we now know a little bit of the scale on this graph. Where do we hit that peak at 24.15 seconds? Now we're interested, okay, what's the greatest height? So for the greatest height, what am I going to be looking at? Am I looking at the height at time 0? Am I looking for the height that's equal to 0? Am I looking for the velocity where the velocity is 0? So one more choice. Am I looking for the velocity at 0, or am I looking for the height at that point where the velocity was 0? Time. Now, all of these things we could find. We could find the height at 0. But the height at 0 is our height right here. We could find where the height is 0 by solving where this function is equal to 0. We don't really want to know the velocity where the velocity is 0, because the velocity where the velocity is 0 is, well, it's 0. So we do want to know where the velocity is 0, but then we don't look at the velocity, we go back to the height. This is where the velocity is 0, but I need to know the actual height there. So I'm going to take this 24.15 and plug it back in the function. So E is our answer here. V at 0 is the velocity at time 0. And in fact, if we go the velocity at time 0, that's 128. And the problem, if we go back and look at this problem again, it tells us an initial velocity of 128 feet per second, which matches with what we find here, the velocity at 0. But what we want to figure out is, okay, what is the height at this time where we figured out that we've leveled off? So we looked at the velocity equaling 0 to figure out when we level off. We figure out when we level off, but we've got to go back to the height to figure out, well, what height are we then? And so we pull out our calculator and do this computation. If I did my computation correctly here with the calculator, we get 1,545.66 feet. Which sounds like a lot. This particular problem is posed on, we're on the moon, where there's less gravity. So if you throw something up, it's going to go up a lot higher. It's going to slow down a lot less as it goes up. It will eventually peak, and we figured out how long it takes to peak. And then it will eventually come back down. So as we're working through this problem, we've now addressed B, what's the velocity of the arrow? We didn't determine the velocity at any specific times, but that would just be plugging in specific inputs. So we could figure it out. We figured out when the velocity would be 0. We figured out what's the greatest height the arrow reaches. So the last question is, well, how long would the arrow be aloft? that's kind of the final question in our analysis of this motion. Well, it turns out that there are a number of ways we could do this. So I'm going to just kind of post some ways we could approach this, and I want you to indicate which one you think is not going to be a good strategy for us. So we can double the time from where the velocity is 0. The idea that the time it takes to go up will be the same time it takes to come back down. We can figure out where h of x equals 0. We can figure out where the velocity is 0. So of those three choices, which one is not going to be immediately helpful for us? And the one that's not immediately helpful for us is actually the solve when the velocity is 0. That only gets us halfway there. If we double it, that will work for us. When we were studying parabolas, the straight line going through the vertex is the axis of symmetry. If we know where one zero is, the other zero is on the exact opposite side. So if we can figure out how long it takes to go up, it's going to take the same amount of time to come down. We're assuming any kind of air resistance with that. So however long it takes to go up, that's how long it's going to take to go down. We could double this. So doubling it does work. So 48.3 seconds. Or we could solve this quadratic. When is this quadratic equal to 0? Because that'll tell us when is the position 0. And so if we do that, negative 2.65 x squared plus 128x equals 0, we could factor out an x. So either x is 0, we started off at a height of 0, or this other factor is 0. And we could work through to solve that. X here. So negative 2.65 x equals negative 128. X then is negative 128 over negative 2.65. And we'd end up with the same result of the 48.3 seconds. I could pull out a calculator and show you that computation. But I'm much more interested at this point in what are we doing. I don't think we need to see the calculator do it to finish up the problem. We're just plugging things into the calculator at that point, just like we did here. At this point, we plug things into the calculator. Now, we will do just a little bit with the idea of acceleration. So here's our velocity. In our car, what makes our velocity change? If you want to change how fast you're going, what do? You step on the gas pedal, also known as the accelerator. There's actually another way. How else could you change your speed? Go down a hill. Okay. Brake. A brake. A decelerator, something that would slow you down. Both of those are called acceleration. One's a negative acceleration. You'd have a force working opposite. But the acceleration is the change in the velocity. I mean, if you slam on your accelerator, you sort of feel a jerk because you're changing the velocity really quickly. Or if you go down and ride, the new ride at Silver Dollar City, which shoots you a couple times, the acceleration is very rapid because you're going from 0 to, 50 in 2.3 seconds. Maybe that's powder keg. There's a time, but very rapid acceleration. The change in velocity is the acceleration. Well, if we know our velocity, the change in velocity, well, we take another derivative. So we can take another derivative here. And so if we do that for this particular function, what do we get if we take another derivative? If we take the derivative of the derivative, what do we end up with? So the derivative of this, well, this is just linear. The derivative of a linear function is the slope of the linear function. So our derivative is negative 5.3, which is what most of you said. Which, when we think about it a little bit, the acceleration is always pointed downward. So we shoot something up. We're going in the opposite direction of the acceleration, so we would kind of slow down, kind of like you're in the car going fast and you hit the brake. Or you're going down the road really fast and suddenly you throw it in reverse. Probably not a good thing for the transmission, but you put it in reverse, you won't stop and go backwards immediately. You'll slow down, then you'll stop, and then you'll start going backwards. If you put the acceleration in the opposite direction of where you're going, it'll slow it down, it'll stop, and then it'll start going the other way. And you should get going faster and faster and faster and faster, which is what we discover as well. So in this case, and really with any sort of projectile motion, the acceleration is always down. Which is why when we throw things up, they slow down, they stop, and they come back down. Because we throw them in the opposite direction. Whereas if you just drop them, they come straight down. There's nothing to make them go up in the first place. So there's quite a bit of analysis of motion we could do. So that's another interpretation. Any function we're talking about, we could be interested, well, how's it changing? If it talks any instantaneous rate of change, that's the derivative. If it's position or height, that rate of change is the velocity. If it's something else, it's still an instantaneous rate of change. We still compute it using the derivative. So we don't even necessarily have to know what our function is. If we're talking the instantaneous rate of change for that function, we'll be taking the derivative. And then we'll also use it for the marginal cost or revenue. If we've got the cost given to us to make X units. So we've got some function that's telling us the cost for X units. The derivative is the marginal cost function. And that's the approximate cost to produce the next unit once we've produced X units. And so the idea here is we've got some cost, we're at some point X, where we may or may not know what the cost is to produce X units. The marginal cost is how much does it cost to produce the next unit? Well, technically, we would need to figure out how much does the cost change. So if we produce 101 units minus the cost to produce 100 units, that would be the cost for that 101st unit. The problem is that computation is often too difficult. So what we're going to do instead is, let's look at the marginal cost. What's the slope of the tangent line? C prime of x, which we're calling here the marginal cost. Along the tangent line, if we change the input by 1, the output changes by our slope. And so what the marginal cost is giving us is approximately the cost of the next item. And notice, we don't have to know how much it costs to produce the first 100 to figure out the cost of the 101st, to estimate the cost for the 101st. All we've got to figure out is, what's the derivative at 100? That would be the approximate cost of the next item. The exact cost would be a whole lot harder to figure out. How much did the cost change? Well, since we're only moving 1 unit away from our input, the tangent line's a reasonable approximation there. And in general, it's much easier to figure out. So page 102 gives some other business terms. We can do this with revenue as well. How much revenue we get if we sell 1 more unit. And there is an error on page 104. I forget what the error was in 104. Yeah, I think we've got time to look at 2.4 as well. We've got about 15 more minutes. So it turns out there's some other functions, actually all kinds of other functions we still don't know how to find the derivative of. Simple ones we can do. As they get a bit more complicated, well, the derivative gets more complicated. And so the first complicated one we're going to look at is, well, what if we're building this function not out of adding and subtracting functions or a constant multiple of functions? What if we were actually multiplying functions? Say x times e to the x. That's a function, so is that. Well, if we're multiplying functions, the derivative of the product is the derivative of the first times the second plus the first times the derivative of the second. It is not just take the derivative of both parts and multiply them. It's take the derivative of one part times the other, and then plus the derivative of one part times the other. Make sure you do the derivative of both at some point, but it's a product of the derivative and the other function. So in fact, the example I've got here is x squared e to the x. If we apply this product rule in this case, it's going to be the derivative of x squared times e to the x plus x squared times the derivative of e to the x. What are we going to end up with when we do that? A little bit more time. So for a product, we have to apply the product rule. If it's a product, both of these involve x, it's a product. So it's the derivative of the first times the second, plus the first times the derivative of the second. And if you mix these two up, that's okay. It doesn't really matter which one is first, which one is second. It's the derivative of one times the other plus the opposite of that. So derivative of x squared is 2x Derivative of e to the x is e to the x. We have to keep the power rule straight from how we take the derivative of e to the x. And that one was c here. So it is not just the derivative of the first times the derivative of the second. That's what a has. And the derivative of e to the x is not done with the power rule. We don't bring the power down and decrease the power by 1 if the power happens to be x. There's a different rule for exponentials than there are for powers. But we can come up with our derivative then. So as our functions get more complicated, this is one of the rules we're going to need. So if we're not just adding or using constant multiples, but we're actually multiplying functions, we have to apply the product rule. Similarly, if we have some quotients, so we're not just adding or subtracting, we've got some divisions going on. The derivative of a quotient is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. I think Dr. Bowling sometimes says, low d high minus high d low, draw a line and square below, as a way to kind of remember the order. Because here the order does matter. Since we're subtracting, if you reverse these, you're going to get the opposite sign of what you're supposed to get. Whereas here, if you happen to reverse these, you're still going to get the same two things added. So it is important to remember, how does the order of subtraction work? So if we had, say, this example, 2x minus 3 over 4x plus 7. That's our function. Our derivative then. From the quotient rule, it's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. This one you're going to need even more time, but I'll start the clock here, and I'll go ahead and add some time to start with, because there's a lot involved here as we work through this. Well, one thing it is definitely not, it is not a. It is not just the derivative of the numerator over the derivative of the denominator. We've already started with the quotient rule here. So the derivative of 2x minus 3 is 2. The derivative of 4x plus 7 is 4. multiply things out in the numerator, I get, let's see, an 8x plus 14, and then minus 8x minus 12, over the denominator squared. The 8x's end up canceling here, and we just end up with 26 over 4x plus 7 squared, which is B. Now, as we work with these rules, yes, there's a lot to keep track of, as with exam 1, when exam 2 comes up, which I think is like 2 weeks after we get back, you can have a note card there as well, because I want to make sure you know how to do derivatives, not could you memorize the formulas. So, you would certainly want to have, you know, the product rule, the quotient rule, probably some of the power rules there. The power rules, after you use them a while, they kind of get more natural to use, but product rule I don't think ever does. Quotient rule, you may have noticed I kept looking. I still don't have that naturally memorized. And if I haven't done it for a while, I have to think really carefully, what is the order of subtraction in the numerator? Because I know it's 1 times the derivative of the other, but I want to make sure I get the order right with that. Now you may think, you know, who in the world would ever be interested in quotients? I think I've got one more slide that talks about that just a little bit. And that's, the book gives the example of the average cost. Average in general is, you add up everything and divide by how many? Well, if we've got a cost function, the average cost to produce x units would be the cost of x units divided by x. We get a rational function. The cost function, whatever it happens to be, divided by x, that would be a rational function. So there are some times where you'd be interested in looking at that. They talk about the marginal average cost. But there are just places rational functions come into play. And certainly as we build more complicated functions, we can do products. Also, as we build more complicated functions, we may even encounter compositions. That's a rule we'll look at after spring break. So hopefully you get a chance to look at this at some point before our next meeting, which is about 2 weeks away, after a week of spring break in there.